Hello and welcome to the Sleepy Astronomer. Tonight, we're drifting into one of the most profound questions humans have ever pondered. Will the universe itself ever come to an end? From the gentle mysteries of cosmic expansion to the distant whispers of heat death, we'll explore what scientists believe about the ultimate fate of everything that exists. We'll journey through theories of cosmic endings and beginnings, discover how dark energy shapes the future of space and time, and contemplate what forever might actually mean in a universe that's been surprising us for billions of years. Along the way, we'll find that even the grandest cosmic questions can offer a kind of peace, reminding us that we're part of something so vast and enduring that our everyday worries fade into the gentle perspective of deep time. If you're new to these tranquil cosmic explorations, welcome to our corner of the universe. And if you've travelled with me before through other stellar adventures, it's wonderful to have you back for another journey to the edge of everything we know. Where are you listening from tonight? Perhaps you're settling in somewhere as evening arrives, watching the first stars appear in the darkening sky. Maybe you're finding a quiet moment as the world around you sleeps, or possibly you're in that peaceful space between wakefulness and dreams where the biggest questions feel most approachable. I always love hearing where our cosmic community gathers from. It's a gentle reminder that no matter where we are on this small blue world, we're all passengers together on the same journey through space and time. If tonight's exploration of cosmic endings and eternal mysteries helps you find that peaceful place where wonder meets rest, a like on the video always brightens my day. And if you'd like to join other curious souls who find comfort in contemplating the cosmos, subscribing really does help more people discover these gentle journeys to the edges of knowledge. Your support means more than you know. It helps keep this little corner of the internet a place where we can ask the biggest questions in the quietest voices, where science meets serenity under the vast umbrella of stars. I'm endlessly curious about which cosmic mysteries call to you most strongly, so please share your thoughts in the comments. Are you drawn to questions about time travel, wondering about parallel universes, or perhaps curious about what lies beyond the edge of the observable universe? Maybe you find yourself pondering whether we're alone among the stars, or dreaming about the far future of human civilization. Your suggestions help guide where our gentle spacecraft of curiosity will venture next through the infinite ocean of cosmic questions. Tonight we'll begin here in the present moment, in a universe that's been expanding and evolving for nearly 14 billion years, and then let our thoughts drift forward through unimaginable stretches of time to explore what physicists and cosmologists believe about the ultimate destiny of everything. We'll discover that the question of cosmic endings isn't just about destruction or finality, but about the deeper nature of time, space, and existence itself. We'll find that even contemplating the end of everything can be a surprisingly comforting meditation on our place in the grand cosmic story. We'll explore how the universe might fade slowly into darkness over trillions of years, or perhaps collapse back into the concentrated energy from which it came, or even tear itself apart in a cascade of expanding space that outpaces the fundamental forces holding matter together. But we'll discover that each of these possibilities, however strange they might sound, emerges from the same beautiful physics that governs the stars twinkling outside your window tonight. So find your most comfortable position, whether you're nestled under blankets while the world sleeps around you, stretched out where you can glimpse the night sky, or simply settled somewhere quiet, where your mind can wander freely through the corridors of cosmic time. Take a gentle breath and let's begin our peaceful drift through one of the most profound questions ever asked. A question that paradoxically might help us understand not just how everything ends, but what it truly means for anything to exist at all. There's something almost comical about the human tendency to worry about endings. We fret about deadlines at work, about whether our favourite TV show will be renewed for another season, about running out of milk before the grocery store opens. And here we are, ready to spend the next few hours contemplating the ultimate deadline, the possible end of the entire universe itself. If that's not the most wonderfully human thing to do, lying in bed worrying about events that might unfold trillions of years in the future, I'm not sure what is. But perhaps that's exactly what makes us human in the most beautiful sense. We're the only creatures we know of who can look up at the stars and wonder not just what's out there, but what will happen to all of it someday. A cat doesn't lose sleep wondering whether the universe will end in heat death or a big crunch. A dolphin doesn't pause in its swimming to contemplate the eventual fate of all matter and energy. But we do, and there's something both absurd and magnificent about that capacity. The question of whether the universe will ever end might seem like the ultimate example of worrying about things beyond our control. After all, we're talking about events so far in the future that our sun will have died, our galaxy will have merged with others, and the very atoms in our bodies will have been recycled through countless cosmic processes. Why spend time thinking about something so distant and abstract? Yet this question has captivated human minds for thousands of years, long before we had the scientific tools to approach it with anything resembling rigour. Ancient cultures developed elaborate mythologies about cosmic cycles, worlds ending and beginning again in endless repetition. The Norse spoke of Ragnarok, a twilight of the gods that would consume the world in fire and flood, only for a new world to emerge from the ashes. Hindu cosmology describes vast cycles of creation and destruction spanning billions of years, with the universe breathing in and out like some cosmic organism. These ancient stories weren't scientific in the modern sense, but they reflected something profound about human nature, our deep need to understand our place in the largest possible context. When early humans looked up at the night sky, they saw not just pretty lights, but the stage upon which the entire drama of existence was playing out. They wanted to know how the story began, how it would unfold, and yes, how it might end. The scientific revolution changed how we approach these questions, but it didn't diminish their fundamental appeal. If anything, modern cosmology has made the question of cosmic endings even more intriguing. We now know that the universe had a beginning, what we call the Big Bang, roughly 13.8 billion years ago. The idea that something that had a beginning might also have an ending feels almost inevitable, like a story that demands a proper conclusion. But the universe, as we're learning, doesn't necessarily follow the same narrative rules as human stories. Our intuitions about beginnings and endings are shaped by our experience of living in a world where everything we see eventually comes to an end. Flowers bloom and wither, animals are born and die, mountains rise and erode, even stars ignite and burn out. It seems natural to assume that the universe itself must follow similar patterns. Yet when we dig deeper into the physics, the picture becomes far more subtle and strange. The universe might end, but not in any way that resembles the endings we're familiar with from our everyday experience. Or it might not end at all, stretching on forever in ways that challenge our basic intuitions about time and existence. To understand why this question is so complex, we need to think about what we even mean when we ask whether the universe will end. Are we asking whether all the stars will burn out? Whether all matter will decay? Whether space and time themselves will cease to exist? Each of these possibilities represents a different kind of ending, and our current understanding of physics suggests different answers for each. There's also the question of perspective. From our viewpoint, trapped as we are in the early decades of a single human lifetime, the universe seems vast and permanent. The stars appear unchanging, the laws of physics seem eternal, and the idea that any of this could simply stop existing feels almost unthinkable. But we know that our perspective is limited, like trying to understand the life cycle of a giant redwood tree by examining a single leaf for a few seconds. Consider the strange fact that we exist at all. The odds against the specific arrangement of atoms that make up your body coming together in exactly this way, at exactly this moment in cosmic history, are so astronomically small that they're essentially zero. Yet here you are, listening to these words, thinking these thoughts, wondering about the fate of everything that exists. The universe has somehow organized itself in such a way that it can contemplate its own future. That might be the most remarkable aspect of this entire question. We're not outside observers looking in at the universe from some external vantage point. We are the universe, quite literally, made of the same matter and energy, governed by the same physical laws, participating in the same cosmic story. When we ask whether the universe will end, we're really asking whether this process of cosmic self-awareness will continue indefinitely, or whether it's a temporary phenomenon in the vast unfolding of space and time. Modern cosmology suggests that the universe has been through dramatic changes before. In its earliest moments, it underwent a period of incredibly rapid expansion called inflation, stretching from smaller than a proton to larger than a grapefruit in a tiny fraction of a second. Later, it cooled enough for the first atoms to form, then for the first stars to ignite, then for galaxies to assemble into the cosmic web we see today. Each of these transitions represents a kind of ending and beginning, the end of one cosmic era and the start of another. The universe we inhabit today is profoundly different from the universe of the first few minutes after the Big Bang, or even the universe of the first few 100 million years before stars began to shine. In some sense, the universe has already ended many times, transforming itself into something new, while maintaining the underlying continuity of physical law. This perspective suggests that the question of cosmic endings might be more nuanced than it first appears. Rather than asking whether the universe will simply stop existing, we might ask how it will continue to transform itself, and whether those transformations will eventually lead to a state so different from what we know today that we might reasonably call it an ending. The beautiful thing about approaching this question scientifically is that we're not just speculating or telling stories, though there's nothing wrong with speculation and stories. We're building our understanding on observations of how the universe actually behaves. We can measure the expansion of space, the temperature of the cosmic microwave background radiation, the abundance of different elements, the behavior of distant galaxies. These observations provide clues about the universe's past and constraints on its possible futures. What we've discovered is both humbling and awe-inspiring. The universe is far stranger than our ancestors imagined, filled with dark matter and dark energy, black holes and quantum fields, phenomena that challenge our everyday understanding of reality. But it's also more comprehensible than they might have hoped, governed by mathematical laws that we can discover and test, patterns that reveal themselves to careful observation and rigorous thought. The question of cosmic endings sits at the intersection of what we know and what we can only imagine. We have solid evidence about how the universe has evolved over the past 13.8 billion years, and we can use that evidence to make educated guesses about what might happen over the next 13.8 billion years, or the next 13.8 trillion years, or even longer. But we're also honest about the limits of our knowledge, the assumptions built into our theories, and the possibility that future discoveries might completely change our understanding. That uncertainty isn't a bug in our scientific approach, it's a feature. The willingness to say, "we don't know yet," is what allows science to continue growing and discovering new truths about reality. It's also what makes questions like this so compelling. We're not just reciting established facts, but participating in humanity's ongoing attempt to understand our place in the cosmos. As we drift deeper into this exploration, we'll encounter some truly mind-bending concepts. We'll discuss the heat death of the universe, a scenario where everything gradually reaches the same temperature and motion ceases forever. We'll explore the possibility of a big crunch, where the expansion of space eventually reverses and everything collapses back into a singularity. We'll contemplate the Big Rip, where the acceleration of cosmic expansion eventually tears apart every atom in existence. Each of these scenarios emerges from our current understanding of physics, but each also pushes that understanding to its limits. They're our best attempts to extrapolate from what we observe today to what might happen in the unimaginably distant future. They're works of scientific imagination grounded in mathematical rigor, explorations of possibility rather than certain predictions. And perhaps that's the most comforting thing about this entire question. We're not helpless passengers on a cosmic ship heading toward inevitable doom. We're participants in a process of discovery, members of a species that has developed the remarkable ability to peer into the deepest mysteries of existence and make sense of what we find there. The universe has been surprising us for as long as we've been paying attention, and there's every reason to expect it will continue to surprise us. The story of cosmic endings is still being written by telescopes and particle accelerators, by theoretical physicists and observational astronomers, by anyone who looks up at the night sky and wonders what it all means. But we're getting ahead of ourselves. Before we can explore these various cosmic endings, we need to understand what our current observations tell us about the universe's present state and likely trajectory. And that brings us to one of the most startling discoveries in the history of astronomy, the realization that our universe is not just expanding, but accelerating in its expansion, driven by something we call dark energy, but don't yet fully understand. If you've ever watched a cup of hot coffee slowly cool down to room temperature, you've witnessed the most fundamental process in the universe. The coffee doesn't magically get hotter on its own. It gives up its heat to the surrounding air until everything reaches the same lukewarm temperature. Once that happens, nothing interesting occurs anymore. The coffee just sits there, neither hot nor cold, in perfect thermal equilibrium with its environment. Now, imagine this same process happening to absolutely everything, everywhere, for all time. Welcome to the concept of heat death, which, despite its rather ominous name, might be the most peaceful ending the universe could ask for. The idea of heat death emerged in the 19th century from scientists trying to understand the behavior of heat and energy. They discovered what we now call the second law of thermodynamics, which states that entropy, essentially a measure of disorder or randomness, always increases in any closed system. This law has the distinction of being one of the most depressing discoveries in physics, at least on first glance. It tells us that energy always flows from hot to cold, that ordered systems naturally become disordered, and that this process is irreversible. Your coffee cooling down is entropy in action. The organized high-energy heat in the coffee spreads out into the less organized, lower-energy thermal motion of the surrounding air molecules. The total amount of energy remains the same. Energy is conserved after all. But it becomes less useful, less concentrated, less capable of doing interesting work. The coffee can't use its remaining thermal energy to heat itself back up, any more than you can unscramble an egg or unmix cream from your coffee. Now, if the universe is a closed system, and most physicists believe it is, then the second law applies to everything that exists. All the energy in the universe, from the nuclear fires burning in stellar cores to the kinetic energy of galaxies racing apart from each other, is slowly but inexorably spreading out, cooling down, and reaching toward a state of maximum entropy. This might take a while. We're talking about timescales that make the current age of the universe look like a brief morning coffee break. The heat-death scenario unfolds over timescales measured in Google years. That's a 1 followed by 100 zeros. To put this in perspective, the universe is currently about 13.8 billion years old. Written out, that's 13,800 million years. The timescale for heat-death is so much longer that all the zeros in the age of the universe represent a rounding error compared to a single digit in the heat-death timeline. During this unimaginably vast stretch of time, the universe would undergo a series of gradual transformations, each representing a step toward maximum entropy. The process would begin with events that are almost modest by cosmic standards. Stars would continue forming for perhaps another trillion years, though at an ever-decreasing rate as the universe expands and the raw materials for star formation become more dilute and harder to bring together. Eventually, star formation would cease entirely. The universe would enter what astronomers call the stelliferous era. The age of stars would come to an end. The last red dwarf stars, those dim but incredibly long-lived stellar light bulbs, would continue burning for trillions of years more, slowly fusing their hydrogen into helium with the patient persistence of cosmic misers hoarding their fuel. But even red dwarfs can't burn forever. One by one they would exhaust their nuclear fuel and fade into darkness, leaving behind white dwarf stars, dense hot remnants about the size of Earth, but containing the mass of our Sun. These white dwarfs would continue glowing for an almost incomprehensibly long time, slowly radiating away their stored heat into the expanding emptiness around them. The universe during this period would become an increasingly cold and dark place, lit only by the fading glow of cooling white dwarfs and the occasional flash of matter falling into black holes. Galaxies would still exist, but they would be graveyards of dead stars, held together by gravity but no longer generating new light or heat. As even more time passed, the white dwarfs would cool to the point where they no longer emitted visible light, becoming cold, dark objects that astronomers call black dwarfs. The universe would enter a period sometimes called the degenerate era, where matter exists but is essentially inert, unable to power the kinds of energetic processes that make the universe interesting today. But the second law of thermodynamics is patient and relentless. Even seemingly stable matter isn't immune to its influence. Given enough time, and we're now talking about timescales that dwarf even the stelliferous era, even protons might decay. This is still theoretical. We've never observed proton decay in laboratory experiments. But many theories in particle physics predict that protons, those fundamental building blocks of atomic nuclei, are not actually stable over infinite timescales. If protons do decay, then given enough time, all ordinary matter would gradually dissolve. The atoms in your body, the carbon in planets, the iron in stellar cores, everything would slowly evaporate into a thin soup of electrons, positrons, neutrinos, and photons. The timescale for this process is so vast that it makes our previous estimates look lightning fast. somewhere around 10 to the 34th to 10 to the 36th years, depending on which theoretical model you prefer. By this point, the universe would consist mostly of black holes of various sizes, from stellar mass black holes formed from collapsed stars to supermassive black holes that once lurked at the centers of galaxies. These black holes would be the last bastions of organized matter and energy in an increasingly empty and cold universe. But even black holes are not eternal. In 1974, Stephen Hawking discovered that black holes actually emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint. For a black hole with the mass of our Sun, the temperature of this radiation is less than 1/1000th of a degree above absolute zero. But it's not zero, which means black holes slowly evaporate, losing mass and energy to the surrounding space. The evaporation process is maddeningly slow for large black holes. A solar mass black hole would take about 10 to the power of 67 years to evaporate completely. Supermassive black holes with millions or billions of times the mass of the Sun would take correspondingly longer, perhaps 10 to the 100 years or more. During most of this time, the evaporation would be imperceptibly gradual. But as a black hole loses mass, its temperature actually increases, causing it to evaporate faster and faster in its final moments. The end of black hole evaporation would be surprisingly dramatic after eons of gentle decline. In its last second of existence, a black hole would release as much energy as a large star produces in its entire lifetime. But by this point in cosmic history, these final fireworks would be isolated events in a universe so vast and empty that the light from one exploding black hole would likely never encounter any other matter or energy. Once the last black holes evaporated, the universe would enter what physicists call the photon epoch. It would consist almost entirely of a thin, cold gas of photons, electrons, positrons, and neutrinos, all at the same temperature and spreading ever farther apart as space continued to expand. No complex structures could form or persist. No information could be processed or stored. Nothing interesting would happen because there would be no energy differences left to power interesting processes. This is heat death, not a violent explosion or catastrophic collapse, but a gentle fading into perfect, unchanging equilibrium. The universe would still exist, but in a state of maximum entropy where no further change is possible. It would be like a cosmic room temperature that extends throughout all of space and time. There's something almost peaceful about this vision, isn't there? No suffering, no violence, no struggle, just perfect eternal rest. Of course, there would also be no consciousness to appreciate this peace, no life to find meaning in the tranquility, no observers to witness the final state of maximum entropy. But then again, by the standards of cosmic time, the entire history of life in the universe, from the first self-replicating molecules to the last conscious thought, would represent the briefest of interludes in an otherwise eternal calm. The mathematics of heat death are beautiful in their stark simplicity. The universe would reach a state that physicists call thermodynamic equilibrium, where the temperature, pressure, and chemical composition are the same everywhere. In such a state, no energy can flow from one place to another because there are no differences in energy to drive that flow. Without energy flow, no work can be done, no information can be processed, and no change of any kind can occur. Think about what this really means in practical terms. Today, the universe is full of temperature differences. Stars burn at millions of degrees, while the space between them hovers just a few degrees above absolute zero. These differences drive everything interesting: stellar fusion, planetary weather, the circulation of ocean currents, even the biochemical processes in your cells, as you listen to these words. Life itself exists by exploiting energy differences, capturing high-quality energy from sources like sunlight or chemical bonds, and using it to build complex structures before releasing lower-quality waste heat. In a heat-death universe, all these differences would be gone. The temperature everywhere would be the same, incredibly cold, but uniform. No star could shine because there would be no fuel left to burn, and no temperature difference to drive nuclear fusion even if there were. No planet could have weather, because weather requires temperature differences between different regions. No life could exist, because life requires the ability to extract useful energy from the environment, and useful energy only exists when there are energy differences to exploit. The concept of heat death was first articulated by the German physicist Rudolf Clausius in the 1850s, though he called it the thermal death of the universe. Clausius was working out the implications of the newly discovered laws of thermodynamics, and he realized that if entropy always increases, then the universe must be heading toward a state of maximum entropy from which no further change would be possible. This realization caused quite a stir in Victorian society. Here was science, which had been revealing the clockwork precision of celestial mechanics and the ordered beauty of natural law, suddenly suggesting that everything was doomed to end in cosmic stagnation. The idea troubled even scientists. Lord Kelvin, one of the giants of 19th century physics, found the prospect so disturbing that he spent considerable effort looking for ways to avoid this conclusion. But the second law of thermodynamics is remarkably robust. Despite more than a century of additional discoveries in physics, quantum mechanics, relativity, particle physics, cosmology, the basic insight remains unchanged. In any isolated system, entropy tends to increase over time, and if the universe is indeed an isolated system with nothing beyond it to exchange energy with, then its ultimate fate appears to be thermal equilibrium. What makes this scenario particularly poignant is how gradual and peaceful it would be. There would be no dramatic moment when the universe dies. Instead, there would be an almost imperceptibly slow fade, like a photograph left in bright sunlight slowly bleaching until the image disappears entirely. The last stars would dim over trillions of years. The last black holes would evaporate over even longer timescales. By the time the universe reached true heat death, the transition would have been so gradual that if there were any observers left, which there wouldn't be, they might barely notice when the final threshold was crossed. There's also something democratizing about heat death. In this scenario, every atom, every particle, every quantum of energy would eventually reach the same final state. The hydrogen that once burned in the core of a massive star would end up at the same temperature and energy level as the hydrogen that once floated in the cold depths of intergalactic space. The carbon atoms that make up your body right now would eventually reach the same thermal equilibrium as the carbon in distant asteroids. In death, if not in life, the universe would achieve perfect equality. The timescales involved also put our current cosmic moment into a peculiar perspective. If the universe were a 24-hour day and heat death occurred at midnight, then the entire history from the Big Bang to now would occupy roughly the first nanosecond after dawn. All of human history, all the rise and fall of civilizations, all the art and science and love and loss that fills our lives, would be compressed into a period so brief it would be invisible on this cosmic timescale. Yet during that brief flash of cosmic dawn, matter managed to organize itself into stars and galaxies, planets and life, consciousness and culture. The universe discovered how to think about itself, how to create beauty, how to ask questions about its own nature and future. From the perspective of heat death, this might seem like an insignificant interlude in an eternity of thermal equilibrium. But perhaps it's more accurate to say that heat death provides the backdrop against which the remarkable improbability of our existence becomes clear. It's worth noting that this scenario assumes our current understanding of physics remains accurate over these enormous timescales. We're extrapolating the laws of thermodynamics far beyond the regimes where we've tested them, and it's entirely possible that new physics could intervene. Perhaps there are processes we haven't discovered yet that could restart the cosmic engines, or perhaps the universe itself undergoes phase transitions that we can't currently imagine. Some theoretical physicists have speculated about mechanisms that might allow the universe to escape heat death. Perhaps vacuum decay could trigger a new Big Bang. Perhaps quantum tunneling could allow the universe to transition to a lower energy state, effectively restarting cosmic evolution. Perhaps the discovery of new forces or particles could reveal pathways around the seemingly inexorable march toward maximum entropy. These are speculative ideas, grounded more in mathematical possibility than observational evidence, but they remind us that science is always provisional, always open to revision based on new discoveries. The heat death scenario represents our best current understanding of cosmic evolution, not a guaranteed prediction of the future. Some physicists have speculated about quantum fluctuations that might, given infinite time, randomly assemble organized structures out of the thermal equilibrium. In principle, random molecular motion could occasionally produce complex patterns, perhaps even, after waiting an incomprehensibly long time, patterns complex enough to constitute conscious observers. These Boltzmann brains would be momentary statistical flukes in an otherwise dead universe, conscious thoughts arising from cosmic noise like faces briefly appearing in clouds. But these are speculations piled upon speculations, mathematical possibilities, rather than realistic expectations. The overwhelming likelihood, based on our current understanding, is that heat death represents a true ending, not of space and time themselves, but of any possibility for complexity, change, or meaning. Yet even this most final of endings contains a strange sort of hope. Heat death only occurs if the universe continues expanding forever, with space growing larger and matter growing more dilute until nothing can interact with anything else. But what if the expansion doesn't continue forever? What if gravity eventually wins the cosmic tug-of-war against expansion, pulling everything back together into a cosmic collapse? That possibility, known as the Big Crunch, offers a very different kind of ending, one where the universe dies not in cold isolation but in hot reunion, with all matter and energy crushed back into the dense, energetic state from which it all began. If heat death is the universe's equivalent of slowly falling asleep and never waking up, then the Big Crunch is more like having such an intense dream that you forget you're dreaming at all, instead of everything gradually cooling down and spreading apart until nothing interesting can happen anymore. The Big Crunch envisions a cosmos that eventually reverses course, with all matter and energy rushing back together in a final, spectacular reunion that would make the Big Bang look like a gentle warm-up act. The idea of the Big Crunch emerged naturally from Einstein's equations of general relativity, which describe how space, time, matter, and energy all interact with each other. These equations allow for multiple possible fates for the universe, depending on how much stuff it contains and how fast it's expanding. Think of it like throwing a ball into the air. Whether it falls back down depends on how hard you throw it and how strong gravity is. Throw it gently and it arcs back down. Throw it hard enough and it escapes to space forever. In the cosmic version of this scenario, the ball is the expansion of space itself, and gravity is the combined gravitational pull of all the matter and energy in the universe. If there's enough matter to provide sufficient gravitational attraction, then the expansion that began with a Big Bang might eventually slow down, stop, and reverse into a big crunch. It's a beautifully symmetric idea. What began in expansion ends in contraction. What started with matter and energy flying apart concludes with everything coming back together. For much of the 20th century, determining which fate awaited our universe was one of cosmology's biggest questions. Scientists work to measure two crucial quantities: how fast the universe is expanding and how much matter it contains. The relationship between these numbers would determine whether we live in an open universe that expands forever, a closed universe that eventually crunches, or a perfectly balanced, flat universe that expands forever but gradually slows down. The measurements were maddeningly difficult to make with precision. Determining the expansion rate required observing distant galaxies and measuring both their distances and their speeds as they recede from us. But measuring distances to faraway galaxies is notoriously tricky. It's like trying to determine how far away a light bulb is when you don't know how bright it's supposed to be. And measuring the total amount of matter in the universe was even more challenging, especially since most of the universe's matter appears to be the mysterious dark matter that doesn't emit light and can only be detected through its gravitational effects. For decades, the measurements seem to hover tantalizingly close to the boundary between expansion and contraction. Some observations suggested the universe might have just barely enough matter to eventually halt its expansion. Others indicated it might expand forever. The uncertainty was frustrating, but it also added a certain existential suspense to cosmology. Humanity was living in a universe whose ultimate fate was genuinely unknown, waiting for better telescopes and more precise measurements to reveal whether everything would end in fire or ice. The Big Crunch scenario itself unfolds like a cosmic movie played in reverse. Initially, the process would be imperceptible. The expansion of the universe would gradually slow down over billions of years, like a ball thrown upward reaching the peak of its arc. For a long time, galaxies would continue moving apart, stars would keep shining, and life could presumably continue evolving and thriving, blissfully unaware that the cosmic expansion was gradually decelerating. Eventually, though, the expansion would come to a complete halt. This moment, the cosmic equivalent of a ball hanging motionless at the peak of its trajectory, would mark the universe's maximum size. From our perspective, it would probably be an entirely unremarkable moment. Individual galaxies would still be moving in various directions due to their local gravitational interactions, but the overall expansion of space itself would have ceased. And then, slowly at first, the universe would begin to contract. Space itself would start shrinking, bringing galaxies closer together. This wouldn't happen quickly. The initial contraction phase might last tens of billions of years, giving plenty of time for stars to live out their natural lifespans and for new generations of stars to form from recycled stellar material. As the contraction continued, however, the universe would begin to heat up. This might seem counterintuitive. After all, when you compress something, shouldn't it get colder? But cosmic expansion actually cools the universe by stretching out electromagnetic radiation, while contraction would have the opposite effect, compressing radiation and making it more energetic. The cosmic microwave background radiation that fills the universe today would gradually shift from microwave frequencies toward infrared, then visible light, then ultraviolet, becoming steadily more intense. During this phase, the night sky would gradually become brighter and more colorful as the cosmic background radiation heated up. Eventually, the background temperature of space would become warmer than the surfaces of stars, fundamentally changing the energy balance that governs stellar physics. Stars would no longer be able to radiate away their excess heat, causing them to swell and eventually be disrupted by the increasingly energetic environment around them. As the contraction accelerated, galaxies would begin merging with increasing frequency. The orderly cosmic web that characterizes our current universe, with galaxies arranged in filaments and sheets separated by vast voids, would collapse into an increasingly dense and chaotic environment. Galaxy collisions, which are relatively rare events today, would become commonplace as space continued to shrink. The final phases of the Big Crunch would unfold with dramatic speed. As matter became more and more compressed, gravitational effects would intensify, accelerating the collapse. The cosmic background radiation would become so energetic that it would start breaking apart atomic nuclei, reversing the nuclear processes that built up heavy elements in stellar cores over billions of years. The universe would literally begin to uncook itself, breaking complex nuclei back down into protons and neutrons. In the last moments before the final singularity, temperatures and densities would approach the extreme conditions that existed in the earliest instance after the Big Bang. The distinction between matter and energy would break down as particles were accelerated to enormous energies. The very structure of space-time would begin to fluctuate wildly as quantum effects became important on cosmic scales. Finally, everything would collapse into a singularity, a point of infinite density and temperature where the laws of physics as we understand them would cease to apply. It would be the Big Bang in reverse, all of cosmic history compressed back into a single, mathematically incomprehensible point. There's something almost poetic about this scenario. The universe would complete a perfect cycle, returning to the state from which it emerged. Every atom, every photon, every bit of information that had ever existed would be compressed back into the primordial fire from which it came. In some sense, the Big Crunch represents the ultimate recycling program. Nothing would be wasted, nothing would be lost forever to the cold emptiness of infinite expansion. Some cosmologists have speculated that the Big Crunch might not be a true ending, but rather a cosmic reset button. Perhaps the collapse into a singularity would be followed by another Big Bang, creating a new universe with new galaxies, new stars, and new possibilities for complexity and life. This cyclic model of cosmology envisions an eternal sequence of expansions and contractions, Big Bangs and Big Crunches, each cycle potentially lasting hundreds of billions of years. In this oscillating universe model, we might be living in just one cycle of an infinite series. Perhaps there were universes before ours that lived and died in previous cycles, and perhaps there will be universes after ours in future cycles. Each universe would have its own unique history, its own galaxies and stars, its own evolution of complexity, and possibly its own emergence of life and consciousness. The oscillating model raises intriguing questions about information and continuity between cycles. Would any trace of our current universe survive the crunch and re-emerge in the next cycle? Would the fundamental constants of physics remain the same, or might they change from cycle to cycle? Could consciousness or intelligence somehow persist through the transition, or would each cycle represent a completely fresh start for cosmic evolution? These questions venture into highly speculative territory, since they depend on physics that operates in regimes far beyond our current understanding. The conditions near a cosmic singularity would involve such extreme temperatures, densities, and gravitational fields that our current theories of physics simply break down. We have no reliable way to predict what might happen during the transition from crunch to bang, or whether such a transition is even possible. The philosophical implications of the Big Crunch are quite different from those of heat death. Instead of everything gradually fading away into cold emptiness, the Big Crunch offers a kind of cosmic apotheosis, a final moment of maximum intensity where everything that has ever existed comes together in ultimate unity. There's something almost mystical about the idea that every atom in your body might someday be reunited with every other atom that has ever existed, compressed together in a singularity that transcends space and time. From a practical standpoint, of course, the Big Crunch would be even more thoroughly terminal than heat death. At least in the heat-death scenario, matter continues to exist even if it can't do anything interesting. In the Big Crunch, matter itself would be crushed out of existence, along with space, time, and any possibility of future existence. It's the ultimate example of going out with a bang, rather than fading away with a whimper. The Big Crunch also offers a different perspective on the significance of our current cosmic epoch. If the universe is destined to contract and collapse, then we're living during the expansion phase of a finite cosmic cycle. This might make our existence seem more precious and unique. We're participants in a cosmic experiment that will run for a specific, limited duration before everything resets. But here's where the story takes an unexpected turn. While the Big Crunch remained a viable possibility for decades, observations made in the late 1990s dramatically changed our understanding of cosmic expansion. Instead of slowing down as scientists expected, the expansion of the universe appears to be accelerating. This discovery was so surprising that it earned the 2011 Nobel Prize in Physics, and it fundamentally altered our thinking about the universe's ultimate fate. The acceleration appears to be driven by something cosmologists call dark energy, a mysterious component of the universe that acts like a kind of anti-gravity, pushing space apart rather than pulling it together. If dark energy continues to dominate cosmic evolution, then the universe will expand not just forever, but at an ever-increasing rate. This would rule out the Big Crunch entirely, but it opens up an even stranger possibility for cosmic ending. What if the acceleration doesn't just prevent gravitational collapse, but becomes so intense that it eventually overcomes all the forces that hold matter together? What if the universe doesn't just expand forever, but expands so rapidly that it tears apart galaxies, stars, planets, and eventually atoms themselves? This scenario has a name that perfectly captures its dramatic nature: the Big Rip. If the Big Crunch is the universe's equivalent of a dramatic finale, where everything comes together in a crescendo of cosmic unity, then the Big Rip is more like a gentle song that gradually becomes so loud it tears the speakers apart. It's perhaps the strangest of all possible cosmic endings. Not a collapse back to a beginning, not a slow fade into thermal equilibrium, but an accelerating expansion so intense that it eventually overwhelms every force in nature, pulling apart first galaxies, then stars, then planets, then molecules, and finally atoms themselves. The Big Rip emerges from our growing understanding of dark energy, that mysterious component of the universe that appears to be driving the acceleration of cosmic expansion. To appreciate how bizarre this scenario is, we need to understand just how unexpected the discovery of cosmic acceleration was. For most of the 20th century, cosmologists assumed that the expansion of the universe must be slowing down. After all, every bit of matter in the universe is gravitationally attracted to every other bit of matter, so gravity should be acting like a cosmic brake, gradually slowing the expansion that began with the Big Bang. This assumption seemed so reasonable that when two teams of astronomers set out in the 1990s to measure how much the expansion was slowing down, they weren't questioning whether it was slowing down, they were just trying to measure the rate of deceleration. They studied distant supernovae, using these stellar explosions as standard candles to determine how fast the universe was expanding at different times in its history. What they found was the astronomical equivalent of dropping a ball and watching it fall upward. Instead of slowing down, the expansion of the universe was speeding up. The most distant supernova, and therefore the oldest since their light has taken billions of years to reach us, showed that the universe was expanding more slowly in the past than it is today. Somehow, cosmic expansion was accelerating. This discovery was so unexpected that both research teams initially thought they had made an error. They spent months checking their calculations, recalibrating their instruments, and looking for any possible source of systematic error that could explain their results. But the conclusion was inescapable. The universe's expansion is accelerating, driven by some form of energy that acts opposite to gravity, pushing space apart rather than pulling it together. Scientists call this mysterious component dark energy. Though the name tells us more about our ignorance than our knowledge, we don't know what dark energy actually is, how it works, or why it exists. We only know that it appears to make up about 70% of the total energy content of the universe, and that it has the remarkable property of causing space itself to expand at an accelerating rate. The simplest model for dark energy treats it as a property of space itself, what physicists call a cosmological constant. In this model, every cubic meter of empty space contains a fixed amount of dark energy that doesn't dilute as the universe expands. As space grows larger, more dark energy appears to fill the new volume, providing an ever-increasing push that accelerates cosmic expansion. But dark energy might be more complicated than this simple model suggests. It could be dynamic, changing over time, or it could have properties that become more extreme as the universe evolves. Some theoretical models suggest that dark energy might not just cause steady acceleration, but could eventually dominate the universe so completely that it tears apart the very fabric of space and time. This is where the Big Rip comes in. In the most extreme models of dark energy evolution, the acceleration of cosmic expansion doesn't just continue, it intensifies. The dark energy becomes more powerful over time, causing space to expand faster and faster until the rate of expansion becomes infinite. At that point, space would be stretching so rapidly that it would overcome every other force in the universe. The timeline for the Big Rip depends on exactly how dark energy behaves, but some models place it roughly 22 billion years in the future, less than twice the current age of the universe. That might sound like a comfortably distant deadline, but it's remarkably soon compared to the timescales for heat death, or even the Big Crunch. We're talking about cosmic catastrophe on what are, by astronomical standards, relatively human timescales. The process would unfold in stages, each more dramatic than the last. Initially, the accelerating expansion would gradually overcome the gravitational forces that hold large-scale structures together. Galaxy clusters, those vast collections of hundreds or thousands of galaxies bound together by gravity, would be the first casualties. The space between galaxies would expand so rapidly that their mutual gravitational attraction could no longer hold them together. Individual galaxies would then find themselves increasingly isolated in an expanding sea of empty space. The Milky Way and Andromeda, which are currently approaching each other and are expected to merge in about 4.5 billion years, might instead be carried apart by the accelerating expansion before they could complete their cosmic dance. As the expansion continued to accelerate, it would begin to affect smaller and smaller structures. Eventually, the expansion would overcome the gravitational forces that hold individual galaxies together. Stars would be torn away from their galactic homes. flung into the growing emptiness between what used to be galaxies. The beautiful spiral arms and elliptical shapes that characterize different types of galaxies would dissolve as their component stars were scattered across space. But the cosmic demolition wouldn't stop there. Given enough time and sufficient acceleration, the expansion would become so rapid that it would overcome the gravitational forces that hold individual star systems together. Planets would be ripped away from their parent stars, sent careening through space as cosmic orphans. The Earth, if it still existed by this point, would be torn away from the Sun and flung into the darkness of interstellar space. The pace of destruction would accelerate as the expansion itself accelerated. Eventually, the rate of spatial expansion would become so extreme that it would overcome not just gravitational forces, but the electromagnetic forces that hold atoms and molecules together. Chemical bonds would be stretched beyond their breaking point as the space between atoms expanded faster than light could travel between them. At this stage, solid matter would simply disintegrate. Rocky planets would crumble into dust as the electromagnetic forces holding their crystal structures together were overwhelmed by expanding space. Biological molecules would be torn apart, making any form of life impossible, even if it had somehow survived the earlier phases of cosmic destruction. In the final moments before the Big Rip, even atomic nuclei would be torn apart as the expansion overcame the strong nuclear force, the most powerful force in nature, responsible for holding protons and neutrons together in atomic nuclei. The very atoms that make up matter would disintegrate, leaving only isolated subatomic particles scattered across a space, expanding so rapidly that they could never interact with each other again. Finally, the expansion would overcome even the forces that hold individual particles together. Protons and neutrons would be ripped apart into their constituent quarks. Space itself would expand at an infinite rate, creating what physicists call a finite time singularity, a point where the laws of physics break down, not because everything is compressed into infinite density, as in the Big Crunch, but because everything is pulled apart with infinite force. The Big Rip represents the ultimate triumph of expansion over all other forces in the universe. It's a scenario where space itself becomes so dynamic, so aggressively expanding, that nothing can maintain its structural integrity. From the largest galaxy clusters down to the smallest subatomic particles, everything would be torn apart by the sheer violence of expanding space-time. There's something almost absurd about this scenario when you think about it. We're used to thinking of empty space as passive, just the stage upon which the drama of matter and energy plays out. But in the Big Rip, space itself becomes the destroyer, expanding so aggressively that it overwhelms every force that allows structure and complexity to exist. The philosophical implications are quite different from those of heat death or the Big Crunch. In heat death, everything gradually runs down and stops working, but matter continues to exist. It just can't do anything interesting. In the Big Crunch, everything is crushed together into ultimate unity. But in the Big Rip, the very possibility of things existing is eliminated. There can be no structures, no patterns, no information, because the expansion of space prevents any two particles from maintaining a stable relationship with each other. It's worth emphasizing that the Big Rip is still quite speculative. It depends on dark energy having very specific properties that become more extreme over time. Most cosmologists consider it a less likely scenario than continued acceleration leading to heat death, but it remains a possibility that can't be ruled out with our current understanding of dark energy. The observational evidence for cosmic acceleration is solid, that much is well established, but the detailed properties of dark energy and how it might evolve over cosmic time remain deeply mysterious. Dark energy could be constant, as in the simplest models, or it could change in ways that lead to the Big Rip, or it could evolve in completely unexpected directions that we haven't yet imagined. Some models suggest that dark energy might even reverse course, weakening over time and allowing gravity to eventually halt cosmic expansion and trigger a big crunch. Others propose that dark energy might oscillate, creating cycles of acceleration and deceleration that could lead to periodic cosmic events unlike anything in our current models. The uncertainty surrounding dark energy reflects a deeper limitation in our understanding of the universe. Despite all our advances in cosmology, we still don't know what makes up about 95% of the universe. The dark matter and dark energy that dominate cosmic evolution, but interact so weakly with ordinary matter that we can only detect them through their gravitational effects. This ignorance is both humbling and exciting. It means that our current models of cosmic evolution, including scenarios like the Big Rip, are provisional, our best attempts to understand the universe based on incomplete information. Future discoveries could dramatically change our picture of how the universe will end, or even whether it will end at all. The Big Rip also highlights the strange role that empty space plays in modern physics. Far from being a passive void, space appears to be an active participant in cosmic evolution, capable of expanding, contracting, and possibly even tearing apart everything that exists within it. This dynamic view of space-time, which emerges from Einstein's general relativity and quantum field theory, represents a profound departure from our everyday intuitions about the nature of space and time. In some ways, the Big Rip is the most thorough of all possible cosmic endings. Heat death leaves matter intact but inactive. The Big Crunch crushes everything together, but might lead to a new beginning. Only the Big Rip eliminates the very possibility of structure and relationship, creating a universe where nothing can exist except isolated particles flying apart at ever-increasing speeds. Yet even this most complete destruction contains elements of uncertainty and possibility. We don't know for certain that dark energy will behave in the extreme way required for the Big Rip. We don't know whether quantum effects might intervene at the smallest scales to prevent the complete dissolution of matter. And we don't know whether the expansion of space can actually become infinite, or whether unknown physics might impose limits on how fast space can stretch. But to understand these uncertainties better, we need to look more closely at the observations that revealed dark energy in the first place, and at what those observations tell us about the current state and future trajectory of cosmic expansion. Measuring the expansion of the universe is a bit like trying to determine how fast a train is moving when you're sitting inside it with the windows painted black. You can't see the landscape rushing by, so you have to get creative about finding clues. In cosmology, those clues come from light, specifically from observing how the light from distant galaxies has been stretched by the expansion of space during its long journey to reach us. The story begins with Edwin Hubble working at the Mount Wilson Observatory in the 1920s with what was then the world's largest telescope. Hubble was studying distant galaxies, trying to determine how far away they were and how fast they were moving. What he discovered changed our understanding of the universe forever. Nearly every galaxy he observed was moving away from us, and the more distant galaxies were receding faster than the nearby ones. This relationship, now known as Hubble's law, provided the first evidence that the universe itself is expanding. The galaxies aren't moving through space. Space itself is stretching, carrying the galaxies along like raisins in a rising loaf of bread. The more space there is between us and a distant galaxy, the more that space has expanded during the light's journey, and the faster the galaxy appears to be receding from us. Hubble's discovery was revolutionary, but it was only the beginning. Throughout the 20th century, astronomers worked to refine measurements of cosmic expansion, trying to determine not just how fast the universe is expanding today, but how that expansion rate has changed over time. This is where the detective work becomes particularly clever. When we look at distant objects in space, we're seeing them as they were in the past, because light takes time to travel. The most distant galaxies we can observe appear to us as they were billions of years ago, when the universe was much younger. By measuring the expansion rate at different distances, and therefore at different times in cosmic history, astronomers can construct a timeline of how cosmic expansion has evolved. The key to these measurements lies in understanding how the expansion of space affects light itself. As light travels through expanding space, its wavelength gets stretched along with the space it's traveling through. This stretching shifts the light toward redder wavelengths, a phenomenon called cosmological redshift. The amount of redshift tells us how much space has expanded since the light was emitted, while the brightness of the source can tell us how far away it is. But here's where things get tricky. Measuring distances in space is extraordinarily difficult. You can't exactly send a tape measure to a distant galaxy. Instead, astronomers rely on standard candles, objects whose intrinsic brightness is known, allowing distance to be calculated from their apparent brightness. It's like determining how far away a light bulb is when you know its wattage, but can only measure how bright it appears from where you're standing. The breakthrough that led to the discovery of dark energy came from using a particular type of stellar explosion, called Type 1a supernovae, as standard candles. These explosions occur when a white dwarf star accumulates material from a companion star until it reaches a critical mass and detonates in a thermonuclear explosion. Because the trigger for these explosions is always the same critical mass, Type Ia supernovae all have very similar intrinsic brightness, making them excellent standard candles for cosmic distance measurements. In the 1990s, two independent research teams, the Supernova Cosmology Project and the HISA Supernova Search Team, began systematic surveys of distant Type Ia supernovae. Their goal was to measure how the expansion of the universe had changed over cosmic time. Based on theoretical expectations, they expected to find that expansion was slowing down due to the gravitational attraction of all the matter in the universe. What they found instead was completely unexpected. The distant supernovae were fainter than predicted, indicating they were farther away than expected based on their redshift. This could only mean one thing. The expansion of the universe was not slowing down as anticipated, but was actually accelerating. Space was expanding faster today than it was billions of years ago. This discovery was so surprising that both teams initially suspected they had made errors in their observations or analysis. They spent months checking and rechecking their data, looking for any possible source of systematic error that could explain the unexpected results. But the conclusion was inescapable. Cosmic expansion is accelerating, driven by some unknown form of energy that acts opposite to gravity. The researchers dubbed this mysterious component dark energy, acknowledging both its invisibility and our profound ignorance about its nature, unlike ordinary matter and energy, which become more dilute as the universe expands. Dark energy appears to maintain constant density even as space grows larger. This means that as the universe expands, the total amount of dark energy increases, providing an ever stronger push that accelerates cosmic expansion. Current observations suggest that dark energy makes up about 70% of the total energy content of the universe. Another 25% consists of dark matter, mysterious particles that don't interact with light, but reveal their presence through gravitational effects. The remaining 5% is ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and everything we can directly observe, including ourselves. This inventory of the universe is both humbling and extraordinary. We live in a cosmos where 95% of the content is completely mysterious to us. It's as if we're trying to understand a symphony while being able to hear only one instrument out of 20. The fact that we've learned as much as we have about cosmic evolution, despite this fundamental ignorance, is a testament to the power of scientific observation and reasoning. The discovery of cosmic acceleration has profound implications for the ultimate fate of the universe. If dark energy continues to dominate cosmic evolution, then the universe will expand forever, growing larger and colder, until it eventually reaches the heat death we discussed earlier. The Big Crunch scenario, which requires gravity to eventually overcome expansion, becomes impossible if dark energy maintains its current influence. But the properties of dark energy remain deeply mysterious, and different models make different predictions about how it might evolve over time. The simplest model treats dark energy as Einstein's cosmological constant, a fixed property of space itself that maintains constant density as the universe expands. In this model, cosmic acceleration would continue indefinitely, leading eventually to heat death. However, dark energy could be more dynamic than this simple model suggests. Some theories propose that dark energy is not constant, but changes over time, either growing stronger or weaker as the universe evolves. If dark energy grows stronger over time, it could lead to the Big Rip scenario we discussed, where acceleration becomes so intense that it tears apart all structures in the universe. Alternatively, if dark energy weakens over time, gravity might eventually regain the upper hand, potentially leading to a big crunch after all. Some models even suggest that dark energy could oscillate, creating cycles of acceleration and deceleration that might repeat indefinitely. The challenge is that measuring the detailed properties of dark energy requires extremely precise observations of very distant objects. We need to detect tiny differences in brightness and redshift that can reveal how cosmic expansion has changed over billions of years of cosmic history. This is at the very edge of what's possible with current technology, requiring space-based telescopes and years of careful observations. Several major observational programs are currently underway to study dark energy in greater detail. The Dark Energy Survey has mapped hundreds of millions of galaxies to trace how cosmic structure has evolved over time. The European Space Agency's Euclid mission is designed to measure the shapes of billions of galaxies to study how dark energy affects the growth of cosmic structure. NASA's future Nancy Grace Roman Space Telescope will conduct even more precise measurements of distant supernovae and other cosmic phenomena. These observations are gradually improving our understanding of dark energy, but the picture remains frustratingly incomplete. We can measure its effect with increasing precision, but we still have no idea what dark energy actually is, or why it exists. It could be a property of space itself, as Einstein's cosmological constant suggests, or it could be a new field permeating the universe, or it could be evidence that our understanding of gravity itself needs modification. The mystery of dark energy highlights how much we still don't know about the fundamental nature of reality. Despite centuries of scientific progress, we find ourselves confronting phenomena that challenge our basic understanding of space, time, matter, and energy. It's both humbling and exciting, a reminder that the universe still holds profound secrets waiting to be discovered. From a practical standpoint, the dominance of dark energy means that the most likely fate for our universe is continued expansion and eventual heat death. The acceleration of cosmic expansion makes it increasingly unlikely that gravity will ever overcome the outward rush of space, ruling out the Big Crunch scenario for all practical purposes. But the precise details of how this expansion proceeds depend critically on the properties of dark energy, which remain largely unknown. Will the acceleration continue at its current rate, leading to a gradual approach to heat death over countless eons? Will it intensify, leading to the violent dissolution of the Big Rip? Or might dark energy surprise us again, evolving in ways that create entirely new possibilities for cosmic evolution? The uncertainty reflects a deeper truth about the scientific enterprise. Our understanding of the universe is always provisional, always subject to revision based on new observations and discoveries. The scenarios for cosmic ending that we've been exploring, heat death, Big Crunch, Big Rip, represent our best current attempts to extrapolate from what we observe today to what might happen in the unimaginably distant future. But science advances by testing these extrapolations against new observations, and the universe has a history of surprising us. The discovery of cosmic acceleration was just such a surprise, completely overturning our expectations about the universe's fate. Future discoveries could be equally revolutionary, revealing new physics that fundamentally changes our understanding of how the cosmic story will unfold. This uncertainty might seem frustrating, but it's also what makes cosmology so compelling. We're not just cataloguing known facts about a static universe. We're participants in an ongoing process of discovery, exploring questions that push the boundaries of human knowledge and understanding. As we continue our exploration of cosmic endings, we need to consider not just the physics of expansion and dark energy, but the deeper question of what it means for anything to end in the context of the universe itself. After all, the concept of ending assumes the existence of time. But what if time itself has properties that we don't fully understand? When you think about the end of something, the last page of a book, the final note of a song, the moment when your morning coffee cup is empty, you're implicitly thinking about time as a kind of cosmic stage upon which events unfold in orderly sequence. Things begin, they happen, they end, and time itself just ticks along imperturbably in the background. But what if this intuitive picture of time is incomplete, or even fundamentally wrong? What if asking whether the universe will end is a bit like asking what colour Wednesday is, a question that seems reasonable until you examine its assumptions more carefully? Our everyday experience of time is remarkably consistent and seemingly straightforward. We remember the past, but not the future. Causes precede their effects. Eggs break when dropped, but never spontaneously reassemble. Time appears to flow in one direction only, from past through present toward future, carrying us along whether we like it or not. This experience is so universal and immediate that it feels like a fundamental truth about reality itself. But physics tells a more complicated story. In the equations that describe the fundamental laws of nature, from Newton's mechanics to Einstein's relativity to the quantum field, theories that govern subatomic particles, time appears as just another coordinate, like length, width, and height. These equations work equally well, whether time runs forward or backward. If you could somehow reverse the motion of every particle in the universe, the laws of physics would be perfectly happy to run the cosmic movie in reverse. This reversibility creates what physicists call the arrow of time problem. If the fundamental laws of physics don't distinguish between past and future, why does our experience of time have such a strong directional character? Why do we remember yesterday but not tomorrow? Why do broken eggs stay broken instead of spontaneously reassembling? The answer appears to lie in the second law of thermodynamics, that same principle we encountered when discussing heat death. Entropy, the measure of disorder or randomness in a system, tends to increase over time. This isn't because the fundamental laws of physics prefer disorder, but because there are vastly more ways for things to be disorganized than organized. A scrambled egg represents just one of countless possible arrangements of its constituent molecules, while an unscrambled egg represents a much more specific, orderly arrangement. The tendency for entropy to increase gives time its arrow. We remember the past because our brains store information in ordered patterns that represent lower entropy states, while forgetting represents the natural tendency for these patterns to decay into higher entropy randomness. We see eggs break and stay broken because broken eggs represent higher entropy states than whole eggs, and systems naturally evolve toward higher entropy. But this connection between entropy and the arrow of time raises profound questions about cosmic endings. If time's direction is fundamentally tied to the increase of entropy, what happens when the universe reaches maximum entropy? In the heat-death scenario, when everything has reached thermal equilibrium and no further entropy increase is possible, does time itself cease to have meaning? This isn't just a philosophical puzzle. It touches on deep questions about the nature of existence itself. If time is defined by change, and change becomes impossible in a maximum entropy state, then the heat-death scenario might represent not just the end of interesting events, but the end of time as a meaningful concept. The universe would still exist, but in a timeless state where nothing can happen because nothing can change. Einstein's theory of relativity adds another layer of complexity to our understanding of time and endings. According to relativity, there's no universal now that applies throughout the universe. Two events that appear simultaneous to one observer might occur at different times for another observer moving at a different velocity. Time itself is relative, dependent on motion and gravity, in ways that our everyday experience doesn't reveal. This relativity of time has strange implications for cosmic endings. If the universe ends in a big crunch, different observers would experience the final collapse at different rates, depending on their motion relative to the collapsing matter. If it ends in heat death, different regions of the universe might reach maximum entropy at different times, as measured by different observers. The ending itself becomes observer-dependent, lacking the universal character that our intuitive notion of ending seems to require. Quantum mechanics introduces even stranger possibilities. At the quantum level, particles can exist in superposition states, where they have multiple possible properties simultaneously until they're observed or measured. Some interpretations of quantum mechanics suggest that the universe itself might exist in superposition states, with multiple possible histories and futures coexisting until some form of cosmic measurement forces it to choose a particular path. In this quantum view, the question of whether the universe will end might not have a definite answer. The universe could exist in a superposition of ending and not ending, of heat death and big crunch and big rip, until some cosmic observation collapses the superposition into a single reality. But what could possibly serve as an observer capable of measuring the entire universe? The question verges on the mystical, touching on deep puzzles about the relationship between consciousness, observation, and physical reality. Some physicists have proposed even more radical possibilities. What if time itself had a beginning with a Big Bang, not just as a practical matter of when things started happening, but as a fundamental property of reality? In this view, asking what happened before the Big Bang is like asking what's north of the North Pole, a question that seems meaningful but actually violates the assumptions built into the question itself. Similarly, cosmic endings might represent not just the cessation of events within time, but the end of time itself. In the Big Crunch scenario, space and time might be crushed out of existence along with matter and energy. In certain models of the Big Rip, the accelerating expansion of space could become so extreme that it tears apart the very fabric of space-time, ending not just the possibility of events, but the temporal framework within which events could occur. These possibilities challenge our most basic intuitions about existence and ending. We're accustomed to thinking of endings as events that happen at particular times. The moment when a star runs out of fuel, the instant when a civilization falls, the second when a person takes their last breath. But cosmic endings might not be events in this familiar sense. They might be transitions to states so fundamentally different from our current reality that concepts like time, event, and happening lose their meaning entirely. There's also the question of whether time itself might be more fundamental than we currently understand. Some theories in quantum gravity suggest that space-time, the unified framework of space and time that Einstein described, might not be fundamental, but rather an emergent property of something more basic. Just as temperature emerges from the random motion of molecules, space-time might emerge from the interactions of more fundamental entities that we don't yet understand. If this is true, then cosmic endings might not represent the destruction of a fundamental aspect of reality, but rather a transition to a different kind of existence where space-time doesn't apply. The universe might end in the sense of ceasing to have the properties we associate with physical reality, while continuing to exist in some more fundamental form that transcends our current concepts of space, time, matter, and energy. These ideas venture far beyond what we can test with current scientific methods, but they illustrate how cosmic endings force us to confront the deepest questions about the nature of reality itself. When we ask whether the universe will end, we're not just asking about the fate of stars and galaxies, but about the ultimate nature of existence, time, causation, and meaning. Consider, for instance, how our understanding of time has evolved throughout human history. Ancient peoples often conceived of time as cyclical, seasons repeating, generations following familiar patterns, cosmic ages cycling through eternal repetition. The linear view of time that feels so natural to us today, with its clear progression from past through present to future, is actually a relatively recent development in human thought, influenced by Judeo-Christian traditions and later reinforced by the scientific revolution. But even our modern linear conception of time might be incomplete. Some cosmological models suggest that time itself could be cyclical on the largest scales, with universes being born, evolving, and dying in endless cycles that stretch far beyond our current cosmic horizon. In such models, what we call the end of our universe might be more like the end of a single day, a transition to something new rather than an absolute cessation. The relationship between consciousness and time adds another layer of complexity to these questions. We experience time in a remarkably specific way, as a flowing river carrying us from past to future, with the present moment representing a kind of moving boundary between what has been and what is yet to come. But this experience of temporal flow might be more about how consciousness works than about how time itself actually behaves. Some philosophers and physicists have argued that the flow of time is an illusion created by the way conscious minds process information. From this perspective, past, present, and future all exist equally, what physicists call the block universe model, and our sense of moving through time reflects the limitations of consciousness rather than a fundamental property of temporal reality. If this view is correct, then cosmic endings might not represent moments when things stop happening, but rather boundaries in a timeless landscape that conscious observers happen to encounter in a particular sequence. This raises fascinating questions about what it would mean for consciousness itself to end. If the universe evolves toward heat death, and the last possible forms of complex information processing gradually shut down as available energy dwindles, does time lose its subjective character even if it continues objectively? Without conscious observers to experience the flow of time, does the distinction between past, present, and future become meaningless? The quantum mechanical picture adds even more strangeness to these considerations. In quantum mechanics, measurement plays a fundamental role in determining physical properties. Before measurement, quantum systems exist in superposition states that include multiple possibilities simultaneously. The act of measurement forces the system to choose a specific state from among the possibilities. Some interpretations of quantum mechanics suggest that consciousness might play a special role in this measurement process. If this is true, then the ending of all consciousness might represent a kind of cosmic transition, where the universe loses its ability to choose specific states from quantum superpositions. The universe might continue to exist, but in a fundamentally different way, neither definitively ended nor definitively continuing, but suspended in a quantum limbo of unrealized possibilities. Of course, these ideas remain highly speculative, and many physicists reject the notion that consciousness plays any special role in quantum mechanics. But they illustrate how questions about cosmic endings inevitably lead us into deep waters, where physics, philosophy, and metaphysics begin to blur together in ways that challenge our conventional ways of thinking. There's also the intriguing possibility that our entire conception of ending might be fundamentally anthropocentric, a projection of human experiences onto cosmic scales where it doesn't properly apply. We understand endings through our experience of birth and death, beginnings and conclusions, causes and effects. But these patterns might be features of complex systems operating far from thermodynamic equilibrium, rather than universal principles that apply to the cosmos as a whole. The universe might not end in any sense that we would recognize as an ending. Instead, it might undergo transformations so profound that the very categories we use to think about existence — space, time, matter, energy, cause, effect — cease to apply. From our current perspective, such transformations might appear to be endings, but they could represent transitions to forms of existence that we can't currently imagine or comprehend. Consider how radically different the current universe is from the state it was in during the first fraction of a second after the Big Bang. In those earliest moments, matter as we know it didn't exist. Protons and neutrons hadn't formed yet. Even atomic nuclei were impossible in the extreme conditions that prevailed. The fundamental forces that govern physics today — electromagnetism, the strong nuclear force, the weak nuclear force — might have been unified into a single, more fundamental interaction. Yet we don't typically think of the transition from that early state to our current universe as the death of the primordial cosmos. Instead, we see it as cosmic evolution, the universe changing and developing new properties while maintaining underlying continuity. Perhaps what we call cosmic endings will similarly represent evolutionary transitions rather than true terminations. The mathematical structures that underlie our physical theories also raise questions about the nature of cosmic endings. Mathematical objects like numbers, equations, and geometric relationships seem to exist in a realm that transcends physical reality. The equation E equals mc squared doesn't depend on the existence of any particular mass or energy for its validity. It describes a relationship that would remain true even if no physical objects existed to exemplify it. If the physical universe ends in any of the scenarios we've discussed, what happens to the mathematical relationships that describe its behavior? Do the laws of physics cease to exist when there's no longer any matter or energy to obey them? Or do they persist in some abstract realm, waiting to govern new universes that might emerge from quantum fluctuations or other mechanisms we haven't yet discovered? Some physicists and philosophers have suggested that mathematical structures might be more fundamental than physical reality itself, that what we call the universe is actually a mathematical object that exists whether or not it's instantiated in what we think of as physical space and time. From this perspective, cosmic endings might represent changes in which mathematical structures are activated or realized, rather than the destruction of anything fundamental. These questions venture into territory where science, mathematics, and philosophy become almost indistinguishable. We're asking not just what will happen to the universe, but what it means for anything to happen at all. We're probing the foundations of existence itself, trying to understand the relationship between abstract mathematical truth and concrete physical reality. The uncertainty surrounding these deep questions is both humbling and exciting. It reminds us that despite all our scientific progress, we're still puzzling over mysteries that may be more profound than anything we've yet imagined. The universe continues to surprise us, revealing new layers of complexity and strangeness that challenge our most basic assumptions about how reality works. From one perspective, this uncertainty might seem disturbing. If we don't even understand what time is or how endings work at the most fundamental level, how can we hope to answer questions about cosmic fate? But from another perspective, the uncertainty is part of what makes these questions so compelling. We're not just calculating the trajectory of known processes, but exploring the very foundations of existence itself. The various scenarios we've discussed, heat death, big crunch, big rip, represent our best current attempts to extrapolate from what we observe to what might happen in the unimaginably distant future. But they're all based on assumptions about the nature of time, space, causation, and physical law that might themselves be incomplete or incorrect. Future discoveries in physics might reveal that time works differently than we currently think, that space has properties we haven't discovered, that the laws of nature themselves evolve in ways we can't predict. Such discoveries could completely transform our understanding of cosmic endings, revealing possibilities that we can't even imagine with our current conceptual frameworks. This ongoing uncertainty and possibility for discovery is one of the most beautiful aspects of science. We're not passive observers of a predetermined cosmic story, but active participants in an ongoing process of exploration and understanding. Each new observation, each theoretical breakthrough, each moment of insight adds to our picture of how the universe works and what its future might hold. As we near the end of our gentle journey through cosmic endings, it might be worth considering what the mere possibility of asking these questions tells us about our place in the universe. We are, quite remarkably, arrangements of matter and energy that have become capable of contemplating the ultimate fate of all matter and energy. The word forever is one of those deceptively simple concepts that becomes more mysterious the longer you think about it. When a child promises to be your friend forever, or when lovers vow to cherish each other for all eternity, they're invoking something that feels intuitively meaningful, but turns out to be surprisingly difficult to define precisely. Does forever mean for a very long time, or for an infinite amount of time? Does it refer to duration within time, or to something that transcends time altogether? And when we ask whether the universe will last forever, are we asking a scientific question or a philosophical one? Our everyday experience gives us plenty of practice with temporary things, but very little insight into what permanence might actually entail. We watch flowers bloom and wither, see buildings rise and eventually crumble, observe that even the most durable materials eventually wear away. Even the most long-lasting things we can think of, mountains, oceans, continents, are temporary when viewed on geological timescales. The very ground beneath our feet is in constant motion, recycled through processes of erosion, subduction, and volcanic activity that completely reshape the Earth's surface every few 100 million years. Against this background of universal impermanence, the idea of something lasting forever seems almost incomprehensible. Yet physics and cosmology force us to grapple seriously with the concept of eternity, because several of the cosmic scenarios we've been exploring involve processes that continue without end. If the universe expands forever, approaching heat death asymptotically, but never quite reaching it, then forever becomes not just a poetic expression, but a literal description of cosmic duration. But what would it actually mean for the universe to last forever? The question becomes more complex when we consider that lasting implies the continuation of something recognizable over time, a universe that persists for infinite duration, but undergoes such radical transformations that it retains no connection to its earlier states, might be said to continue forever. But in what sense would it be the same universe? Consider the heat death scenario we explored earlier. In this future, the universe continues to exist for infinite time, but in a state of maximum entropy where no change or development is possible. Space keeps expanding, carrying isolated particles ever farther apart, but nothing interesting happens. No stars shine, no planets form, no complexity emerges. The universe persists, but in a way that seems to make the concept of persistence itself meaningless. This presents a curious paradox. We can imagine a universe that lasts forever, but becomes increasingly empty and featureless, approaching a state where its continued existence becomes indistinguishable from non-existence. It's a bit like the philosophical puzzle of the ship of Theseus. If you replace every plank of a wooden ship over time, is it still the same ship? If the universe persists forever, but loses every property that makes it interesting or recognizable, in what sense has it really continued to exist? The mathematical concept of infinity adds another layer of strangeness to these questions. Infinity isn't just a very large number, it's a fundamentally different kind of quantity that behaves in counterintuitive ways. If the universe lasts for infinite time, then any event with a non-zero probability of occurring will eventually happen, no matter how unlikely it might be. This leads to some remarkable conclusions about what forever might contain. In an infinite universe with infinite time, random quantum fluctuations would eventually produce every possible arrangement of matter and energy, no matter how complex or unlikely. Given enough time, fluctuations would randomly assemble copies of Earth, complete with all its history and inhabitants. They would create every possible variation of every possible world, every possible version of every possible life. In a sense, infinite time would contain everything that could possibly exist, repeated infinitely many times, in infinitely many variations. This scenario, sometimes called the eternal return, suggests that if the universe truly lasts forever, then everything that has ever happened or could ever happen will happen again, not just once, but infinitely many times. Every conversation you've ever had, every decision you've ever made, every moment of joy or sorrow you've ever experienced would be recreated in perfect detail somewhere in the infinite expanse of space and time. The idea is both comforting and unsettling. On one hand, it suggests that nothing is ever truly lost. Every moment of beauty, every act of love, every instance of consciousness would be preserved in the eternal repetition of cosmic patterns. On the other hand, it seems to drain individual moments of their specialness and uniqueness. If everything happens infinitely many times, what makes any particular occurrence meaningful or significant? But perhaps this perspective reflects limitations in how we think about meaning and significance, rather than fundamental truths about the nature of value. The fact that there might be infinitely many versions of any given moment doesn't necessarily diminish the reality or importance of the specific moment you're experiencing right now. After all, the knowledge that there are billions of other sunsets happening throughout the universe doesn't make the sunset you're watching any less beautiful. The concept of forever also raises questions about the relationship between time and existence that we touched on in our previous discussion. If time itself is not fundamental but emergent, arising from more basic processes rather than being a basic feature of reality, then asking whether the universe lasts forever might be asking the wrong kind of question entirely. Some theories in quantum gravity suggest that space-time itself might be a kind of average or approximation that emerges from more fundamental quantum processes. Just as temperature emerges from the average motion of molecules but becomes meaningless when applied to individual atoms, time might emerge from quantum interactions but lose its meaning when applied to the universe as a whole. In this view, the universe might not exist in time so much as time exists in the universe, as a property of certain kinds of complex systems, rather than as the stage upon which all existence plays out. If this is correct, then the question of whether the universe lasts forever becomes as meaningless as asking whether the number 7 will still exist next Tuesday. The universe wouldn't end because time ends. Rather, time would end because the kinds of complex processes that give rise to temporal experience would cease to occur. There's also the possibility that forever itself might have different meanings depending on the scale at which we apply it. From the perspective of human experience, even the lifetime of a single star, millions or billions of years, represents a kind of forever that exceeds our capacity for meaningful comprehension. From the perspective of cosmic evolution, however, stellar lifetimes are brief episodes in a much longer story of universal development. Perhaps the universe exhibits a kind of hierarchical structure of forever, with different processes operating on vastly different timescales. Quantum processes occur on timescales of 10 to the negative 23rd seconds. Chemical reactions typically take microseconds to seconds. Biological processes operate on timescales from seconds to centuries. Geological processes unfold over millions to billions of years. Stellar evolution occurs over billions to trillions of years. And cosmic evolution might operate on timescales that make stellar evolution look instantaneous. Each level of this hierarchy might have its own version of forever, duration so long compared to the characteristic timescales of that level that they represent practical eternity. A mayfly that lives for a single day might experience that day as forever, if it were capable of philosophical reflection. A human civilization that lasts for 10,000 years represents forever from the perspective of individual human lives. A galaxy that persists for trillions of years embodies forever from the perspective of stellar evolution. This hierarchical view suggests that questions about cosmic forever might be fundamentally unanswerable from our current perspective, not because we lack sufficient data or computational power, but because we're embedded within timescales that make cosmic forever impossible to comprehend meaningfully. We're like mayflies trying to understand geological time, or bacteria attempting to grasp the concept of seasons. Yet there's something remarkable about the fact that we can even attempt to think about cosmic forever. Despite our temporal limitations, we've developed conceptual tools, mathematics, physics, philosophy, that allow us to reach beyond our immediate experience toward genuinely universal perspectives. We may not be able to truly comprehend infinite time, but we can reason about it, model it mathematically, and explore its implications for cosmic evolution. This capacity for transcendence represents one of the most extraordinary features of consciousness, as it has emerged in our corner of the universe. We are finite beings embedded in temporary processes, yet we can conceive of infinity and eternity. We live for mere decades, yet we can contemplate cosmic processes that unfold over billions of years. We are made of matter that will eventually be recycled through stellar nucleosynthesis, yet we can imagine scenarios where even matter itself decays away. The ability to think about forever might itself be one of the most remarkable things that the universe has produced in its long evolution from simple energy and matter toward increasing complexity. In developing consciousness capable of cosmic perspective, the universe has, in a sense, transcended its own temporal limitations. Through us, and presumably through other conscious beings elsewhere in the cosmos, the universe becomes capable of contemplating its own eternity. This perspective suggests that the question of whether the universe lasts forever might be less important than the fact that the universe has become capable of asking the question. Regardless of which cosmic scenario ultimately proves correct, heat death, big crunch, big rip, or something we haven't yet imagined, the universe has already achieved something remarkable in developing the capacity for self-awareness and cosmic contemplation. From this view, consciousness represents a kind of cosmic awakening, a moment when the universe begins to understand itself. Whether this awakening lasts for millions of years or billions of years or forever becomes less crucial than the fact that it has occurred at all. The universe has succeeded in creating beings capable of appreciating its beauty, understanding its laws, and contemplating its ultimate destiny. This doesn't answer the scientific question of cosmic duration, but it suggests a different way of thinking about cosmic significance. Perhaps the meaning of existence doesn't depend on whether existence continues forever, but on the quality and depth of awareness that existence makes possible, a universe that burns brightly with consciousness, for a finite time, might be more meaningful than one that persists forever in unconscious emptiness. But these reflections on meaning and significance bring us to our final consideration. How should the possibility of cosmic endings affect our understanding of purpose, value, and what it means to live meaningful lives in a universe whose ultimate fate remains uncertain? Here we are, having travelled together through billions of years of cosmic time, from the gentle mysteries of expanding space to the profound questions of what forever might mean, and somehow we've arrived back where we started, in this quiet moment, in this present instant, with you listening to these words and contemplating the vast story we've just explored. It's a bit like taking an enormous journey around the world, only to discover that the most interesting place was your own backyard all along. Except in this case, the backyard happens to be a small blue planet orbiting an ordinary star in an unremarkable galaxy, in a universe full of wonders we're only beginning to understand. Throughout our exploration, we've encountered three possible endings for everything that exists. The slow fade of heat death, where the universe gradually cools into eternal stillness. The dramatic reversal of the big crunch, where everything collapses back into the fire from which it came, and the violent dissolution of the big rip, where accelerating expansion tears apart the very fabric of reality itself. Each scenario emerges from our current understanding of physics, yet each pushes that understanding to its limits, forcing us to extrapolate from observations of today's universe to predictions about a future so distant that our sun will have died and been forgotten long before any of these cosmic endings begin to unfold. The remarkable thing about this scientific journey is not just what we've learned about possible cosmic fates, but what the journey itself reveals about the nature of human curiosity and the strange capacity for transcendence that consciousness brings to the universe. We are, after all, collections of atoms that were forged in stellar cores billions of years ago, organized by 4 billion years of evolution into patterns complex enough to contemplate the ultimate fate of every atom in existence. The fact that matter can become aware of itself, that energy can develop the ability to ask questions about energy, that the universe can evolve beings capable of wondering about the universe's own ending. This might be the most extraordinary aspect of the entire cosmic story. When we trace the timeline of heat-death, we saw how the universe might gradually exhaust its capacity for interesting change, with stars burning out one by one until only fading embers remain in an ocean of expanding emptiness. The process would unfold over timescales so vast that they dwarf not just human history, but the entire history of complex matter in the universe. Yet during this slow fade, there would be ample time for consciousness to spread throughout the cosmos, for intelligence to evolve in forms we can barely imagine, for the universe to explore every possible way of being aware of itself before the final energy gradients disappear and thought becomes impossible. In our exploration of the Big Crunch possibility, we discovered how the universe might complete a perfect circle, returning to the compressed, energetic state from which it emerged nearly 14 billion years ago. This scenario offers a kind of cosmic recycling, where every atom that has ever existed comes back together in ultimate reunion. While current observations suggest this outcome is unlikely, the very possibility reminds us that the universe's story might be more cyclical than linear, with endings that are also beginnings, deaths that lead to rebirths we can't yet comprehend. The Big Rip scenario showed us perhaps the strangest possible ending, where the acceleration of cosmic expansion becomes so extreme that it overcomes every force in nature, pulling apart galaxies, stars, planets, molecules, and eventually atoms themselves. It's an ending that erases not just the contents of the universe, but the very possibility of contents, a dissolution so complete that even the framework for existence disappears. Yet this scenario too emerges from the same physics that governs the gentle expansion we observe today, reminding us how extraordinary outcomes can arise from seemingly ordinary processes given enough time and space to develop. Through our examination of cosmic expansion and dark energy, we saw how recent observations have fundamentally changed our understanding of the universe's trajectory. The discovery that cosmic expansion is accelerating, driven by the mysterious dark energy that makes up 70% of everything that exists, represents one of the most startling surprises in the history of astronomy. It reminds us that the universe is stranger than we imagined, and probably stranger than we can imagine, full of phenomena that challenge our most basic assumptions about how reality works. Our investigation of time and endings revealed how even our most fundamental concepts become mysterious when examined closely. The idea of an ending assumes the existence of time, but time itself might be more complex, more malleable, more dependent on the existence of change and complexity than our everyday experience suggests. If the universe reaches a state of maximum entropy where no further change is possible, does time itself cease to have meaning? If space expands so rapidly that it tears apart the very structure of space-time, does the concept of ending even apply? These questions push us beyond the boundaries of current scientific understanding into philosophical territory, where physics and metaphysics become almost indistinguishable. When we contemplated what forever might mean, we discovered that infinity is not just a very large number, but a fundamentally different kind of concept that generates paradoxes and possibilities that stretch our conceptual frameworks to their breaking points. An infinite universe with infinite time would contain every possible arrangement of matter and energy, every possible moment of consciousness, every possible form of beauty and meaning, repeated infinitely many times, in infinitely many variations. This prospect is both overwhelming and comforting. Overwhelming because it seems to drain individual moments of their uniqueness. Comforting because it suggests that nothing beautiful or meaningful is ever truly lost. But perhaps the most important insight from our journey is that asking these questions about cosmic endings might be more significant than finding definitive answers to them. The fact that the universe has evolved beings capable of contemplating cosmic eternity represents a kind of transcendence that transforms the very nature of existence itself. Through consciousness, the universe becomes capable of appreciating its own beauty, understanding its own laws, and wondering about its own future. This capacity for cosmic perspective might be the most remarkable thing that has emerged from 14 billion years of cosmic evolution. The uncertainty surrounding these ultimate questions is not a failure of scientific understanding, but one of its greatest strengths. Science advances by acknowledging the limits of current knowledge while developing tools for pushing beyond those limits. The scenarios we've explored represent our best current attempts to understand cosmic evolution, but they're provisional rather than final, subject to revision based on new observations and theoretical developments that we can't yet anticipate. This uncertainty leaves room for wonder, for continued discovery, for the possibility that the universe will surprise us in ways that completely transform our understanding of cosmic endings. Perhaps dark energy will evolve in unexpected ways. Perhaps new physics will emerge at scales we haven't yet explored. Perhaps consciousness itself will play a role in cosmic evolution that we can't currently imagine. The future remains genuinely open, genuinely mysterious, genuinely full of possibilities that extend far beyond our current conceptual horizons. From one perspective, this uncertainty might seem unsettling. We would like to know what will happen to everything, to have definitive answers about ultimate questions, to understand our place in a cosmic story whose ending we can predict with confidence. But from another perspective, the uncertainty is part of what makes existence wonderful. We live in a universe that is still revealing itself to us, still full of surprises, still capable of generating new forms of beauty and meaning that we haven't yet discovered. The question of whether the universe will end also raises profound questions about how we should live in the face of cosmic uncertainty. If everything is temporary, if even the universe itself might not last forever, does anything we do really matter? Or does the temporary nature of existence make our choices and actions more precious rather than less meaningful? Consider that every act of kindness, every moment of love, every instance of compassion occurs against the backdrop of cosmic impermanence. The fact that nothing lasts forever doesn't diminish the reality of these experiences. If anything, it makes them more poignant and valuable. A flower is not less beautiful because it will eventually wither. A friendship is not less meaningful because it won't last. For cosmic eternities, A work of art is not less moving because the civilization that created it will someday be forgotten. Perhaps meaning doesn't require permanence. Perhaps the significance of existence lies not in its duration but in its depth, not in its eternal persistence but in its capacity for generating moments of awareness, understanding, beauty, and connection. The universe might end, but that doesn't erase the fact that it has already succeeded in creating phenomena of extraordinary richness and complexity. Galaxies and stars, planets and life, consciousness and love, science and art, all the magnificent expressions of cosmic creativity that have emerged from the simple expansion of space and the gradual cooling of primordial energy. We are participants in this cosmic creativity, temporary arrangements of matter and energy that have somehow become capable of appreciating the beauty and mystery of the process that created us. Every moment of consciousness represents a small victory over entropy, a brief triumph of organization and complexity in a universe that tends toward disorder. Every act of understanding represents the universe coming to know itself more deeply. Every experience of wonder represents reality becoming aware of its own extraordinary nature. The cosmic perspective we've explored tonight doesn't diminish the importance of human-scale concerns and joys. If anything, it provides a context that makes them more precious. Knowing that we exist during a brief window of cosmic history when complexity and consciousness are possible makes every day, every relationship, every moment of awareness a gift we might otherwise take for granted. Our journey through cosmic endings has also revealed the profound interconnectedness of all existence. The atoms in your body were forged in stellar cores, scattered through space by supernovae, and gathered by gravity into the planet where life could emerge and evolve. You are quite literally made of star stuff, connected to every other bit of matter in the universe through a history that stretches back to the Big Bang itself. The carbon in your muscles, the oxygen in your blood, the calcium in your bones, all of it participates in the same cosmic story that governs the evolution of galaxies and the expansion of space. This interconnectedness extends beyond physical matter to encompass the very possibility of understanding itself. The scientific knowledge we have explored tonight represents humanity's collective attempt to comprehend our cosmic context. Every observation, every theory, every moment of insight contributes to a growing picture of how the universe works and where it might be heading. We are all participants in this grand project of cosmic understanding, contributing our small part to the universe's ongoing effort to know itself. As our gentle exploration draws to a close, it's worth reflecting on how remarkable it is that we can have these conversations at all. We began with a simple observation that sometimes sleep seems elusive on bright moonlit nights, and we've travelled through billions of years of cosmic evolution to contemplate the ultimate fate of everything that exists. This capacity for intellectual journey, for following questions wherever they lead, for finding connections between the most immediate personal experiences and the most abstract cosmic possibilities, this might be consciousness's greatest gift to the universe. The cosmos has spent nearly 14 billion years evolving from simple energy and matter to the complex structures we see around us today. Through life and consciousness, it has developed the ability to reflect on its own nature and destiny. Whether the universe ends in fire or ice, in collapse or expansion, in dissolution or eternal persistence, it has already achieved something remarkable in creating beings capable of asking these questions and finding them meaningful. So as you drift towards sleep tonight, perhaps under the gentle light of that same moon that connects us to the tidal forces and cosmic rhythms that have shaped our world, you might carry with you this sense of cosmic connection and wonder. You are part of a story so vast and ancient that it encompasses everything that has ever existed, yet so intimate and immediate that it includes this very moment of awareness, this particular arrangement of thoughts and feelings that is uniquely yours. The universe will continue its expansion into the unknown future, carrying with it all the complexity and beauty it has created during its long evolution from simplicity toward consciousness. And for this brief moment in cosmic time, you are part of that ongoing creation, a temporary but meaningful expression of the universe's capacity for awareness, understanding, and wonder. Rest well, fellow travellers through space and time. The cosmos keeps its patient watch over us all, unfolding its mysteries at scales both vast and intimate, reminding us that we are not separate from the universe, but participants in its grandest adventure, the slow, remarkable journey from energy to matter to life to consciousness, to questions that reach toward the very foundations of existence itself. Sweet dreams under the cosmic sky, and may your wonder never end, even if the universe someday will. Thank you for joining me on this peaceful exploration through the deepest questions we can ask. Until we meet again under starlit skies, may your rest be deep, your dreams be filled with cosmic perspective, and your sense of connection to the infinite bring you gentle peace. Clear skies and boundless curiosity, the Sleepy Astronomer.